All right, so as we introduce the integral in Chapter 11, be reminded that, as I've mentioned before, in calculus there's two main branches, differential and integral. And we have been moving through differential calculus, covered a lot of its applications and how to work with functions and their derivatives and what that means. And now we're going to be looking at something called the integral. The integral is connected to what we've done in Chapter 10, and Chapter 9 when we talked about the antiderivatives. So if we just flip back to the notes here real quick, Chapter 9 we learned about antiderivatives. And so in essence we've been going from a function to its derivative, right? And we've learned how to do that, and we've learned also what this means, okay? Lots of different aspects to the derivative. In Chapter 9 we went backwards to something called the antiderivative, and that would be sort of the parent function that when you take the derivative of the antiderivative, you get the function back, right? That's what we did in Chapter 9. In Chapter 10, we connected the antiderivative, and we connected that to an area under a curve, and of course that curve is f of x. And we learned that the area function really could be evaluated, and if we're talking about under a positive curve from a to b, the area function using the antiderivatives of f of x, we could say that if we evaluate the antiderivative at the b value and we subtract the antiderivative at the a value, really what we're doing is we're saying, okay, the antiderivative is the area between this value and the y-axis here, all the way back to 0, and underneath this upper curve. And then a, of course, would be the area from a back to 0. And so you get this area between a and b by doing the subtraction. And so that's what we did in Chapter 10. And now Chapter 11, we introduced something called the integral. So before I get to all this, okay, I'm going to hop back to the textbook, and you can join me on your textbook there too. You guys are on page 94. All right. So notice that in 11.1 we're talking about the definite integral. So a little bit of a review from a previous class. But if we're talking about the area underneath a curve, we can visualize this. Visualize, is that a word? We can visualize this or envision this as the sum of areas of very small rectangles that would fit underneath the curve. Now these would be large rectangles, and obviously there's bits and pieces here of this that seem to be, okay, that's not under the curve, this is not under the curve. So taking 10 rectangles like you see here is not a good idea. But as we talked about yesterday, what if we actually split each of these into 100 or into 100 rectangles, and so we had 1,000 rectangles? Well, then it would be a real good approximation of the area under the curve. And so if we think about this, there's some new notation that I want to introduce to you, and I guess we can sort of start here. Talked about this the other day as well, but just a quick refresher. The definite integral, definite means we're looking for an actual number answer. Okay? Definite integral means we have a value, and that's why we can connect the definite integral with the area under the curve here. Okay? So area under the curve involves antiderivatives, and what we're going to see is actually the area under a curve. One of the ways you can define what an integral is. Okay, so just like if you think back to Chapter 2 and 3 and 4, we were talking about instantaneous rate of change as a derivative, right? Or the slope of a tangent line was actually a derivative. Well, now we're kind of connecting the area under a curve as the integral. Okay, so that's our first basic connection. It doesn't have to be just that. It's not limited to just that, but that is one of the ways of thinking about it. So let's see. The first thing that we notice is different is this elongated S. Okay, it's an elongated S. It's not an F. Okay, it's not a fancy F. It's an elongated S. And why is that used? Because the integral is seen as a sum, and this Greek letter sigma, this is the uppercase sigma, in math and science means sum. Okay, and so this is S for sum. And what are we adding, or what are we taking the sum of? Well, the areas of all these rectangles. Okay, and we can thank Riemann for that. But anyways, this we aren't going to deal much with this. Okay, we're not going to talk about the area under the curve in terms of limits. Okay, that's for another time. You'll see that that's sort of going back to basics, which we're not going to do. We're going to kind of skip that a little bit, but we're going to talk directly about integrals. Okay, so the rest of this stuff you don't have to really worry about. But the terms here are important. So this elongated S is called the integral sign. Okay. The f of x, the actual function, is called the integrand. A and b are the limits of integration, where a is the lower limit and b is the upper limit. Okay. Oh, for some reason all right. And this whole thing, the integral, this whole package should be regarded as one single symbol, or kind of like sine of x, right? It's not two parts, not sine times x, so it's not really the integral sign times f of x times d of x. Don't think of it that way. The significance of d of x will be explained later when we start to talk about methods of integration and how that kind of works. But calculating an integral is called integration, just like calculating a derivative is called differentiation. Okay? Now, so as I mentioned just a few minutes ago, the big connection between an integral and antiderivatives are that this integral represents the area under the curve. All right? And if we go back to chapter 10, the area under the curve was a difference of antiderivatives, right? The antiderivative of the function expresses a difference. Okay? And yeah, so that's kind of what we're making the connection to here in chapter 11. Right, so this integral, okay, let's see. This area function, this integral right here, really is this whole thing. That's basically what this is. And this is the main point of section 11.2, the fundamental theorem of calculus. Okay, so this is the fundamental theorem of calculus. That the definite integral, and we'll just redo it down here, the definite integral with limits of integration from a to b of f of x dx is actually equal to the antiderivative of x evaluated at b minus the antiderivative of f of x evaluated at a. Okay? So, area under the curve, area under the curve. This is a definite integral because we actually have limits to it, and we are talking about an actual number. Okay? It's a definite integral. These are the same thing. They're equal to each other. So what I'm saying is that if I give you this, okay, what I'm actually asking for is the area under the curve for the function x cubed between -1 and 2. And how we do that is we find the antiderivative of this, right? And you evaluate that from a to b. Do you remember this notation here? Okay, I think I talked about this notation before, but this might be new, which actually means this. Okay, so there's an example of what I mean. And sorry. If I'm being consistent here, let's change the a and b to the actual numbers we have here. So from -1 to 2. Okay, and this one is 2, and this one is -1. Okay, is it just a change in notation? It would be like this, Matt. Okay, it would be like this. The limit as h approaches 0 of f of a plus h minus f of a, right, all over h. That's actually the derivative, right? So I'm talking about the same thing. I'm talking about the exact same thing. Now, there are special rules to go from the derivative, or from the function to the derivative, right? You don't have to bypass this to get here, right? If you're given f of x. You can go straight here with some special rules, right? So right now, what we're doing, though, is I'm saying that if you're given this, this is what you do right here, okay? Now, so it's just a progression, okay? So again, we talked about antiderivatives, right? If we go back to this section up here, talked about antiderivatives. Then we explained how to use antiderivatives to find the area under the curve. Now we're calling the area under the curve the integral. That's it. That's it. That make sense? That help? Okay. And that's it. Yeah. So it's not really anything new. In a sense, it's just new notation. Yeah. But we're trying to connect what we've been doing with what integrals actually are. Okay. Now, I want to explain something because I know I've talked to you guys about the fact that if we're trying to find the area between, in this case, we're trying to talk about the area between the graph and the x-axis. We've talked about this being a positive area, and this being a positive area, and this being a negative area, right? And that's when we were talking about an upper function, right? The f of x up top, and then the lower function, f of x on the bottom, right? And we always said that, hey, we're going to get a positive area if we take the upper function and we subtract the lower function, okay? So, now, and this is going to take a little bit of thinking. I had to think through this example myself. It's not in the textbook, but this is a question that I have, okay, or had. Like, why is this? If we can just take the integral of the function, because you notice this right here, there's no consideration for, is this above 0, is this greater than 0, or is this less than 0? There's no consideration to that at all. And you'll see that as they develop this, that the integral, it doesn't matter when it's above the x-axis or when it's below, it all works out. And so you can find the area between the graph and the x-axis using the integral of the function. But I wanted to explain why that's not a big deal when we talk about if this is a negative area and this is a positive area. Because it looks like these would almost cancel each other out. Like it looks like the area here, right, should be approximately equal to 0. Right? Because we have two little positive pieces and we have one big negative piece. But that's not the case. It's not the case when we're talking about integrals, and here's why. Okay? This area right here, let's say that this is f of x, and this is y equals 0. That's the x-axis, right? Y equals 0. And so before, if we wanted to find the area, we would have to go f of x minus 0 to get the area under the curve, right? Between the curve and the x-axis. What we had been doing before, if this was a separate section, then we would go, okay, the upper function is 0, and we subtract f of x. And that would give us a negative area, right? But what happens if we treat f of x, okay, as the upper function in this case, and we subtract the lower function? Then what? Well, then we get a positive area, okay? I should put positive there. Positive area. So this is what I'm going to say. Before, this was the upper function for this area, this was the upper function for this area, and this was the upper function for this area. That made this positive, it made this negative, and made this positive. But if I don't treat